We're going to be looking at interrupts, the role of interrupts, and interrupt service routines, and the role within the FD cycle. Now, in order to fully understand interrupts, we need to be able to clearly define what they are. And here's a little example of how they are used. So I've got my CPU, and it's connected to a number of devices, a hard drive, a timer, and the keyboard. And let's say I press a key on the keyboard. Now, the CPU doesn't know that this has happened, so I need to be able to tell the CPU that, hey, someone's pressed a key. So I need to be able to send a message from the keyboard over to CPU. And we call that message an interrupt, because it's interrupting what's currently happening with the CPU. So electric signal is sent from the device over to CPU to say, something needs to happen, you need to do something about it. In order to fully understand this, we need to kind of break it down into the sections. So, interrupts will get set in something called the interrupt register. So inside the CPU, there's a special register called the interrupt register. Whenever a interrupt occurs, a bit within that register gets set. Okay. So here you can see I've got an example of an interrupt register. This is an example. It's not the one, And each bit represents a different type of interrupt. So the timer interrupt might be in the first bit, a keyboard in the second bit, and different devices for the other ones. So the flag represents whether interrupt has occurred and not whether it's been dealt with or not. Okay. Also, if I press more than one key, for example, then only a single bit will be changed. It's not going to have a number in there. So, for example, if I press 4 keys, I have the number 4 in there. It's always going to be 1 and 0. 1, it's happened. 0, it hasn't. So we call the number here an IRQ, or interrupt request. Okay, and this interrupt register. So let's actually see an example. So I press a key on the keyboard, and interrupt passes from the keyboard to the CPU. When that happens, a bit within the interrupt register is set. Okay, so the IRQ1 is linked with the keyboard, so I set the bit there to be 1 to say, okay, that's happened. So here's a good opportunity to take a little bit pause, because the entire mechanism behind interrupts, interrupt service routines is quite involved, and there's quite a lot to think about, so it's best to break this up into little stages. So define what is meant by an interrupt, and list out 4 examples of interrupts, and then describe what happens when an interrupt is sent from a keyboard. Now, I've included a little word cloud here just to ensure you get the detail on that one. So interrupt, flag, bit, IRQ, and register. So at the end of the FE cycle, the interrupt register is checked. Okay, so this happens all the time to see whether actually anything else needs to be done. If an interrupt has been set, then the operating system needs to be notified about this. So the OS would then make a decision based on the priority of what to do next. So if the current running process has a higher priority, then we ignore the interrupt for a bit. We let that higher priority process run. If, on the other hand, the interrupt has a higher priority, then we're going to deal with the interrupts. If multiple interrupts occur, then we deal with the one with the highest priority. Okay, and that's defined by the operating system and not by us. So here goes the process. So an interrupt occurred, press the key in the keyboard, for example. We set a bit within the interrupt register. The CPU at the end of the FD cycle checks it. And then if the interrupt has a high enough priority, we will then deal with it. And then we have this little mechanism. Now, this mechanism is not part of this spec, so you don't need to know it, but I thought I'd include it just so you can see, well, actually, how do the CPU and the operating system link together on this? Okay, because it's not the CPU itself which deals with interrupts. All the CPU does is let the operating system know an interrupt has occurred. That's its only job. And it does this by using a special table called the interrupt table. And each IRQ will have a memory address of the interrupt service routine used to deal with that interrupt. Okay, so in this case, when a keyboard interrupt was set, we've got an interrupt service routine defined here that memory address, which contains all the software needed to actually deal with it. So it's the operating system is responsible for creating up this table, and it's the operating system then will deal with the interrupts. The CPU kind of just passes it on and say, okay, here's the interrupt, you deal with it, I'm going to get back to doing what I do best. So when an interrupt happens, we need to do something, and we use something called an interrupt handler. It's also known as an ISR, or interrupt service routine. You'll probably will notice in the old spec, interrupt handler was used more. In the new spec, we're going to be using the word interrupt service routine more. Okay, so I thought I'd include both of them just so you are prepared both ways. So interrupt handlers will be set up by the operating system. Okay, the operating system has the responsibility of kind of linking them to each interrupt. The operating system will register an IRQ as part of its initialization with the correct ISR. Okay, so it basically links the interrupt request, so that bit inside the interrupt register, to the correct interrupt service routine via the interrupt table. So it's important that handlers are short and efficient. We don't want interrupts that take ages to process, because otherwise the system will start to hang. And they tend to be written in C or a low-level language, just because we need them to run really, really quickly. So you don't need to know about the interrupt table directly. Okay, you do need to know though that there is a link between an interrupt and an interrupt service routine which gets run as a result of it. Okay, the operating system is responsible for the interrupt service routine. The CPU is responsible for simply saying, here's an interrupt, it's occurred. The operating system needs to deal with it. Okay, so it's the mechanisms of how that works is not on the spec, but you do need to know it happens. Now, so an interrupt happens. We are going to inform the operating system that it's occurred. We now need to do some swapping around. So if I need to run an interrupt, I need to stop and interrupt the current process, and I need to save it, because there's no point me dealing with a key on the keyboard, for example, if I then have to open up, I don't know, for example, Word again from scratch and start it all the way from the beginning of the program. That would be really inefficient. So I need to be able to save the current process. This includes storing the contents of registers. So remember, there's some special registers: the program counter, which keeps track of the next instruction to be executed, the MAR, MDR, the result of the last fetch, CR, the instruction I'm currently running, and obviously the accumulator, because if I'm halfway through a calculation in my program, I need to be able to get back to it. And there are going to be other registers involved as well, which we need to keep track of. All that information gets placed into a special data structure known as the process control block. Now, the exact structure of the process control block is beyond the scope of the A-level. However, knowing that all these registers get saved is important. I think it's important to know that they're saved in something called a process control block, because it kind of makes sense. It's kind of a little package. You can think of it a bit like an envelope. We put everything inside the envelope and then we do something with it. So data about a process will be copied into the process control block by the operating system. Again, it's not the CPU that's doing this, it's the operating system. As each core can only run one process at once, it's important to save enough information that we can get back to it. Okay, so all that information gets saved inside the process control block. Now, once we've created a process control block, we place it into something called a process stack. Now, we haven't really spent a lot of time talking about data structures yet, or maybe you have, I don't know. But a stack is simply a first in, last out, or last in, first out data structure. So the process gets copied from the CPU into the process control block and placed into this process stack, ready to be run again. So we copied the process onto the stack by creating process control block, but interrupts are just processes. They themselves might be interrupted. So if that's the case, we would create another process control block and then place that onto the stack. So if that happens, then we need to restore it once the process is finished. So once I finish the other interrupt, I then copy the other one back onto it, finish off that one, and then finally restore the other one. and we can restore it because it contains all the registers, all the information we need to actually get it back up and running. So here's an important task to do. So you need to draw a flowchart to represent what's happened so far. You need to include in it the interrupt when it first happens, go into the CPU, set in the bit in the interrupt register, then at the end of the FD cycle, the priorities are checked by the operating system. It then will create a process control block, place it onto the process stack, and so on and so forth. So getting all that level of detail into it. Then this second task is really to help explain this idea that when an interrupt occurs, it itself might be interrupted, and then what the process stack might look like. To finish off, just a little bit of subject clarification. So you need to be able to understand the purpose of interrupt. So why do interrupts occur? So why do we need them? And candidates also need to understand why interrupt might be generated and what happens when the interrupt occurs.